Cool. Hi there. So again, thank you for your flexibility. I apologize that I can't be with you. And even more so, apologize that this is going to run like a lecture as opposed to a seminar. So as I've mentioned, I will talk about this material now and give it to you as kind of background, similar to what I would do in class. And then my plan is to really participate in the discussion. So you'll see me popping in there, making comments. Remember that we're not at a point where I am making correctives and stuff like that, right? So I may ask you to think about things a little bit differently or poke and prod and stuff like that. But that is not to say that your comment is incorrect in some way. It is just to say that I'm going to, as a peer would, talk a little bit about what I'm seeing when I'm kind of reading through and working on these texts. All right, anyway, so what are we talking about? We're talking about Hempel in chapters 3 and 4 of Philosophy of Natural Science. And there's a lot of really cool stuff that is going on in these chapters. We built up right from chapters 1 and 2, where we were talking about what it would take in order to accept a hypothesis and what sorts of things might confirm hypotheses. We talked about testing them, right? So once we have an idea of what's going on, the way that we confirm it is by trying to test it. That totally makes sense. But there's still a lot more to that story, right? So we need to talk a little bit more about the way that testing works, some of the different things that we think about when we think about testing, and then really get into the idea of confirmation. So let's get right to it. Obviously, if you have questions about any of this stuff, add that stuff into the discussion as well, and we can go into more detail. So when we get into chapter 3, let me just get to it there. All right, good. So the idea, one of the things that it talks about, the test of a hypothesis, its logic and force. So what can we expect when we're thinking about testing? First off, there is testing, and then there's testing, right? Right on page 20, at the beginning of this, Hempel talks about the differences about different types of tests. We're talking about experimental versus non-experimental tests, for instance. So there are some things that we can test in practice. There are other things that we can test in principle, right? I could test the length of time, or I could have a hypothesis about the length of time between geological ages, right? But I can't actually test that directly through experiment. I can test it indirectly, but I can't test it through experiment because the experiment would take hundreds of thousands, if not millions of years. And I'm old, but I'm not that old. So there's some things that I can't directly test. Hempel is not saying that those are garbage if you can't, right? Indirect tests are absolutely fair game, and they can teach us quite a bit, but they require us to do other sorts of things. We may need to test the implications of something, test something indirectly, right? So we've talked before about electrons. We can't actually see an electron. What we can do is we can see the vapor trails that it leaves in a cloud chamber. So if we want to understand electrons, we can run experiments where we are seeing the impact on those vapor trails. Is that directly experimenting on electrons or on what we can see based on electrons? These are open questions, but we certainly learn a lot about electrons that way. And Hempel is going to say that he thinks that there is something real about electrons, that although we can't see them directly, the fact that we can test them indirectly and that they can be used for other things, and that there does seem to be a continuum between the things that we can see and many things that we can't in the ways that we can test them, that he does consider these to be, they are a thing. So indirect testing, right? Whether something has to do with long periods of time that we can't directly measure, whether it has to do with the specifics of our sensory apparatus. All of these things are interesting, and they can impact what we can expect, what we can predict and what we can take away from tests. But Hempel takes a pretty expansive view on what testing is and how important it is for science. One example of this, which we can talk about later, I think I've mentioned before that there are philosophers that make the argument that our apparatus really is the be-all and end-all when we talk about understanding things, when we talk about having knowledge of things. So that for people like Bos von Frausen, if we did an experiment where I was sitting next to a dog and every time a tone is played, I was told to raise my hand and the dog would bark. The tones get higher and higher and higher until at some point, right, both of us are raising a hand and barking. Well, I'm raising a hand, he's barking. And at some point, the tone is high enough that I can't hear it, but the dog barks. Is there something that is substantively different between the tone that I raise my hand on and the tone the dog is barking on? Is that second tone, is that other tone less real in some way? I mean, it's an interesting question, right? I mean, I have ample evidence for the tone to be there. I can see the button being depressed. I can see the dog, hear the dog barking. I can have the experience of these tones going up in pitch, getting harder and harder to hear them. All of that stuff for me is good evidence that these tones are continuing. So again, testing can have a variety of, can work in a variety of ways. And I've talked in other classes before about laboratory testing and field testing, right? Testing things in the field is a lot messier. It's not controlled. Testing things in the lab is very controlled, but doesn't necessarily represent reality. So there are lots and lots of really cool things that we can talk about in terms of testing. But let's move to a couple of things that Hempel talks about, some specifics. He talks about the role of auxiliary hypotheses. What is an auxiliary hypothesis? Well, when we try to test something, we think, right, especially in the laboratory, that we're testing one thing. We're holding everything else constant and testing one thing. But in fact, it is rare, even in laboratory situations, that we're ever testing just one thing. Because if I'm testing, holding, if I'm testing something, there usually is a lot of other theoretical kind of apparatus that is kind of behind it. And if I get something wrong, it could either be that my hypothesis was wrong or that one of the background assumptions that are surrounding the hypothesis are wrong. So in many cases, we think of testing things as testing bundles, not as testing a single hypothesis, right? The idea of hypothesis bundles, we sometimes call them. What do I mean by that? Well, a great example of this, and this is the thing with Tycho Brahe and Copernicus. So one of the things when we talk about the nature of the, or our place in the universe, right there, and this is something that if you took 215 with me, you've heard this before, so apologies. But back in the day, right, there were two models of the universe: the geocentric model, one where the Earth is at the center of the universe and everything else, including the sun and everything revolving around it, versus the heliocentric model, which has the sun in the middle and the Earth revolving around the sun with the other planets, the moon, et cetera. So obviously we are heliocentrists, right? We believe that we are moving around the sun and that the sun is moving and all that stuff, but whatever. But the point is that heliocentrism had a real problem. And this is something that Tycho Brahe mentioned back in the, was that probably 1600s. And that is that if we are revolving around the sun, then when we're looking at, if I'm looking at a star over here and I'm revolving around the sun, when I'm up here seeing the star and when I'm down here seeing the star's relative position should move, something called parallax, right? Something that I've done as a demo in classes, and you can do it at home safely, right? If you take a thumb, you stick it in front of your face about a foot and close your eye and look at your thumb, and then you wink back and forth looking at your thumb, I'll wait for you to do it. Your thumb appears to move back and forth depending on which eye is winking, and that's because your eyes are in different positions and you're viewing an object from different perspectives. Same thing if I'm looking at a star and I'm revolving around a planet, around the sun, sorry. then the position of that star should be different here versus here. But the problem is that when they looked for parallax, they could not find it. Stellar parallax was considered to be a real problem for heliocentrism because it did not exist. It was discovered 200 years later. And the reason that they didn't discover it in the first place is that there was an auxiliary hypothesis. And that auxiliary hypothesis was that if this is the Earth, the stars are over here, when in fact, the stars are over there. Right? The stars are much, much farther away. And since they are farther away, the further away something is, the less parallax it will demonstrate. So 200 years later, after inventing much, much more fine-grained instruments, they were able to discover that parallax was indeed occurring. So that's why we talk about auxiliary hypotheses, and the idea that we generally test hypotheses, knowingly or not, in bundles rather than in isolation. So it's just something I think that's really kind of interesting, that when we think about testing hypotheses, right, we talk about things in terms of crucial tests, right? And this is something else that Hempel talks about on page 25. The idea of a crucial test is if you have two different possible explanations for what's going on, you lay them out against each other and you find a test where only one of them will come up to be correct, right? True or false, right? Yes or no. So if you lay out two hypotheses and you run a test to determine which of them is correct, that crucial test seems to be implying that we're able to test a single hypothesis at a time. And ideally, that would be lovely. Granted, all that would do would be to show that one of the hypotheses is wrong, right? Does proving you wrong prove me right? No, it doesn't do that at all. And that's a problem. It's something Hempel talks about a little, but it is a real problem with the whole idea of a crucial test. If I prove you wrong, all I've done is prove you wrong. Unless I am able to go through the infinite number of possible solutions, it really does nothing but show me that your answer is not a good answer. It doesn't show that mine is actually very good or that it's correct. And that is for both the reason that, again, I'm showing you wrong just shows you wrong. And additionally, if I do prove you wrong, you may just say, well, actually, I'm still right. All you've done is you've proven one of these other auxiliary hypotheses wrong, and I just need to fix that. And that is common. When people's hypotheses are proven to be wrong, in many cases, people will not drop them. They will try to find ways to fix it. They'll try to find duct tape, right, in order to fix their hypothesis. Now, in the case of stellar parallax, that was a good thing because the stars are, in fact, much further away than we thought they were in antiquity. And if we had gone with parallax not existing, we might still be geocentrists. So yes, sometimes hypotheses need to be re-examined. Yes, auxiliary hypotheses are a thing. And yes, we should be reconsidering them. But at some point, you got to let it go. And if you don't let it go, and if you just keep trying to fix it by any means necessary, right? If your answer to being wrong is to, pull out the duct tape. Yes, I just happen to have duct tape at hand's reach. It says something about me, I know. But right, if that's your answer, there's at some point, there's going to be so much duct tape there that you're not going to be able to see what's going on. It's just a big sloppy mess of duct tape. When that happens, then we consider those hypotheses to be ad hoc. Ad hoc means just stuck on, right? What's the difference between an ad hoc hypothesis and an auxiliary hypothesis? Really, the difference is that if the auxiliary hypothesis does the job and we accept it, then we consider it to be an auxiliary hypothesis. If it all falls apart and we say, this is a load of crap, we're not doing this anymore, then we call it ad hoc. And I'd love to say that there is something more systematic than that, but it really does come down to whether or not we like it or not. If we like it enough, we'll say that this is auxiliary. If we don't, then we just say, oh, this is just stuck on, this is garbage, it's ad hoc, we don't do this. All right. So let's see if we have anything else going in this chapter. One thing that, so we can go through if people would like. I mean, there are just a number of really cool experiments about, we can talk about phlogistotic chemistry. We can talk about Torricelli's barometer. I mean, there's so many good case studies in here that we can talk about that. I'm happy to do that, but I'll leave it for discussion and move into chapter 4, I think. Yeah, criteria of confirmation and acceptability. So surviving a crucial test, right? Being able to show that my hypothesis is better than yours, as I've said, and as Hempel says, is not conclusive proof of anything, right? And the pitfall is, right? Thank you to Activision, right? The pitfall is when you believe that proving you wrong proves me right, or vice versa. The fact is that it doesn't. It proves very little. And the idea of confirmation, the idea of being able to prove that my hypothesis is correct is, I'm not going to say that it's folly, but it is very difficult. You can never prove it 100%. You can never be certain based on positive outcomes, right? Based on testing, because I can't do an infinite number of tests. And if I do the same test, and this is what Hempel talks about, if I do the same test again and again and again and again and again, I'm not going to get much confirmation out of that. It's not going to do a lot of work at telling me that I'm right. Sure, the first time, if I say, hey, universal attraction, and the first time I do a trick like that, okay, that's saying, okay, that proved right what I was thinking about. But if I just keep doing the same thing again and again and again, it's going to lose its power pretty quickly in terms of giving me enough additional information that I'm going to say, wow, and you did it a 300th time versus the 370th time, because that other 70 times really didn't need to happen. So as we say, confirmation is incremental, but it's not linear. It isn't just every time you run a test and win, you get better and better and better and better and better. It just doesn't work that way. So we need to think on a number of different terms. We can think about the quantity of tests, the variety of tests, right? That's something, looking at different sorts of things. So I can try dropping all different sorts of things in order to show my hypothesis to be correct, and doing it in different sorts of ways, going to different locations, doing it at different times. Again, if I'm not sure what's relevant, right? And that's relevance is very important. But if I don't know what's relevant, then I need to try all sorts of things in order to give a variety of cases. And that variety might say, okay, well, it doesn't just work when I do it. If you drop something, it works when you do it. If you're in a different time zone, if you're doing it at night. So none of these different other sorts of factors in terms of where you're living, if you're outside, if you're inside, all of these things, right? In terms of variety. Also precision, being able to measure things and get a really good idea and very clean delineation of the things that are going on. All of these things are ways to help with confirmation. But again, as Hempel says, right, confirmation is not going to be, he says, a favorable outcome of even very extensive and exacting tests cannot provide conclusive proof for a hypothesis, but only more or less strong evidential support or confirmation. There are lots and lots of things to consider. And even this, we're going to see other philosophers that are going to take issue with the idea that surviving challenge in this way provides much of anything in terms of confirmation. Even this, Hempel may be taking things a little bit too strong. But what Hempel is trying to do is he's trying to show that having a variety, having diverse evidence, that all of these things are ways to make it clearer that what you are looking at is the hypothesis you're wanting to look at and not the bundle, not the auxiliary, because this is always the fear, right? As we've just talked about. The idea that you can ever test one hypothesis at a time is really hard to prove. And so as a result, you try all of these different tricks to try to winnow out anything else that could be an auxiliary hypothesis that is, kind of helping you or harming you because you think that it's helping you. Some other things that can be of use or can be of some help to you, right? Which Hempel lists out a couple of things that can, if a hypothesis that you have if your hypothesis is conservative, right? And he talks about this in terms of theoretical support. In other words, if it is implied by other things that are going on, if it makes sense given other things that are happening in the field, that is more reason to believe it, right? If we have a law of gravity, right? And the reason that we really accept the law of gravity is that we also accept the law of universal attraction. Law of universal attraction is that all things in the universe, right, are mutually attracted to all other things in the universe. Gravity makes sense because the Earth is the most massive thing around us. So everything is going to be more attracted to the center of the Earth than it is to all the other things around us. So we don't have to do a lot of extra work on gravity because it already has the theoretical support coming from the other higher order assumptions that we have. Right. So that's why I kind of think of it as conservatism, because it really is saying that if something is in lockstep with things that we already accept, we'll generally believe it. Hempel also talks about simplicity, the idea that if we have two alternatives and one of them has less assumptions behind it or is less complicated, that the simpler one is generally the better one. And the last is just how probable, how credible we think it is. That can come from the source of the hypothesis. It can come from just what we generally think should be the case, right? Again, background assumptions. Now, I'll say that for all three of those, for conservatism, for simplicity, and for credibility, there are real issues with those things, right? Many of our best scientists, a lot of our best science is conservative. Sure, 90% or more is conservative, but then you get Einstein and the theory of relativity. That's not conservative at all. So some really good science is not conservative. Now, Hempel isn't saying to discard it, right? He is saying that it is a favorable thing, right? All things being equal, if your hypothesis is in line with other stuff, it's going to be easier to swallow. And I think that that's probably true. But again, I do want to say that this is not a criterion of adequacy, as others might say, right? This isn't something that says whether something is science or not, because Hempel recognizes, he quotes Einstein all the time, that a lot of science is not conservative. Similarly, simplicity. I mean, I got to tell you, as anyone who's worked with me knows that I don't like that criterion at all, or that idea at all. Simpler isn't necessarily better. Simplicity is a matter of reference. I will think that something is simpler if I think that it's right. So a lot of context goes into simplicity. I think that something has less assumptions if those assumptions are things that I already accept as being true. Talking about heliocentrism versus geocentrism, is it simpler to say that the Earth is standing still or that the Earth is moving around the sun? Right? I would think that having the Earth standing still would be simpler, but people generally argue that simplicity, because of some of the math that we do in order to calculate things like eclipses, is slightly simpler for the heliocentric side of things, the ones that we're on, than the geocentric side. So on one hand, some of the math is simpler for heliocentrism, for the idea that the Earth is spinning around the sun. But in terms of base assumptions, I mean, I don't feel like I'm moving at all, right? I mean, look at the, you're looking at me on a video. Nothing is spinning. Hopefully nothing is spinning. If something is spinning, drugs are bad. Don't do drugs. Anyway, but, right? So which is simpler? It's going to depend on what level you're looking at, what assumptions you have. So again, I would resist simplicity. I don't like it at all, really, as a criterion or way of thinking about things. But again, what Hempel is saying is that all things being equal, right, we generally will trust things that are credible. We generally will trust things that are in line with what we already believe. We'll generally trust things that don't require us to take large leaps outside of our comfort zone. That may say more about us than the hypothesis. And I think that that is really interesting, right? Is it better for the hypothesis? It does make a difference for the hypothesis. The hypothesis is either right or it's wrong. But how much stock am I going to put in it? How much do I think that it's confirmed? Well, that may differ, right? So I think it's interesting to kind of think about things along those terms. All right. So again, there are lots of other things. I'm happy to talk about them. I'll look forward to reading your comments and your responses and to participating in that. But I think that that will probably do for the day. Next time, right, we're going to take a look at chapters 5 and 6. And chapters 5 and 6 work on laws and their role, laws and their role in scientific explanation. I could just read it, right? So the idea of looking at the presence and really kind of foundational need for what Hempel is going to call general laws or covering laws. And these things are going to be incredibly important, foundational. And also in this chapter, in chapter 5, we're going to get Hempel's views on explanation, right? So not just a hypothesis, but how do I know why something has occurred? Right? Description is that something occurred, right? At a particular time, this thing fell. That is description. But asking why does it fall? That is calling for an explanation. Hempel is going to argue that explanations are really the key to science. And those explanations are going to depend on laws and other things. And we're going to talk about what those are. And we're going to figure out why explanations are so important. What do they do for us? And how do they give us science, right? The kind of stuff that when we think about science, we think about it really in terms of explanations. So laws are going to be very important. And we're also going to talk about the role that theories play in explanations in terms of connecting us, making connections between our explanations and kind of the life that we lead. All right, so some really cool stuff, but those are going to be for next time. If you have any questions, please contact me, email me, call me, text me, all these different sorts of things. Get a hold of me, all right? And I'll look forward to seeing you in the discussion forums, and I will see you again for our next class. All right. Don't forget chapters 5 and 6 next time. Stay tuned. Take care.